أعزائي الطلبة، كما وعدتكم في الفيديو السابق، راح اليوم أحل لكم سؤالين من الأسئلة اللي suggested problems. واحد يتعلق بالسynchronous موتور والآخر يتعلق بالسynchronous generator، و they almost cover all the material of this chapter. The first question is problem 6.8. Problem states a three-phase 50 horsepower 2300 volt 60 Hz star-connected synchronous motor has XS 11 ohm per phase. When it draws 165.8 kilowatt, the power angle is 15 degrees. Neglect RA. Determine EF/IA power factor. Part 2, if the mechanical load is thrown off and all losses are negligible, determine the line current and the power factor. By what percent should the field current IF be changed to minimize the line current? Now, first thing we do, as we told you before, when you deal with three-phase system, then this voltage is the line voltage, and in this case, we have to get the phase voltage divided by √3, and so this is the phase voltage. Now the power developed is equal to 3 VT EF divided by XS sine delta, and we are given that the motor draws 165.8 kilowatts, so this is 165.8, which is equal to 3 times 1328 times EF divided by 11 sine 15. We can use this equation for the power because this is the developed power P, but since there are no losses, neglecting R, so this is developed power and the input power is the same, and EF is 1769, and the angle must be negative. As we said before, for the motor the angle is negative. Now EF equal VT minus JIA XS, therefore IA equal VT minus EF divided by JXS, and IA is equal to this quantity divided by 11 angle 90 degrees, that is J, and the result is 41.6 plus J 34.6, which is equal 454.1, and the angle 39.75. The power factor in this case is going to be cosine of this quantity, and is going to be 0.7688, and it is leading because the sign here is plus. If we go to the second part of the question, the second part talks about if the mechanical load is thrown off and all losses are negligible, i.e. the motor is rotating at no load, and there are no losses whatsoever, and he wants determine the line current and power factor. Now, when there are no losses, then there is no need for a developed power. So there's no developed power, there's no losses, so that's the input. There's no need for input power, so Pn is going to equal to 0. Pn is real power. Real power equal to 0. There is another power, we'll see it in a minute. And delta will be equal to also 0. So Ia is going to equal 1328 angle 0 minus 1769 angle 0 divided by 11, and this is equal to minus 40.1 angle minus 90. And as you know from مثلثات trigonometry, the minus I could change it by an angle of 180 degrees, so 180 minus 90 would give me 90 degrees. And the power factor is cosine 90, which is 0 leading. Now, the motor will be acting in this case as a pure capacitor, withdrawing a reactive power which is equal 3 times Vt 1328 time 3 times Vt, that's the times Ia, that will be the reactive power that the motor is drawing or delivering. It's basically acting as a pure capacitor in this case. Now, if we go to the second part of the question, we want the value of the minimum current. Now, the current is given by this equation, and the minimum value for the current is 0. And the current will be 0 if the numerator, البسط, يساوي 0, which means that EF must equal to VT. Now, Vt is constant, it's the supply line voltage. So, EF, we have to reduce EF from the original value of 1769 volts to 1328. Now, EF is proportional to, depends on proportional to EF proportional to IF. So, IF new will be 1328 E divided by 1769. EF new divided by EF old times the IF old, which is equal to 0.75 IF old, i.e. the percent reduction in the field current is 75%. That's the first question, which is deals with the synchronous motor. The second question concerns a synchronous generator. Now, if you look at the wording of the question, it is problem 611, and it is again one of the suggested problem for you. Tell you is a 3-phase 14 kV. Again, this is the line voltage, 10 MVA, the 10 megavolt amp. This is the apparent power, which is S of the machine, 60 Hertz 2-pole, 0.85 power factor lagging, star connected synchronous generator, has XS 20 ohm per phase and RA 2 ohm per phase. in fact, we'll take in one section of the question, we'll consider RA. And can you see the comparison? XS is in here is 10 times RA. Normally, actually, it is much greater than that, especially for this size of a machine. Could reach about 50 times. So you expect if this is a 20, then if it's 50 times, RA will be about 0.4 of an ohm. Anyway, 20 divided by 5 by 50, which is 4%, 4.4. Now, the first part, you want to determine the excitation voltage and torque at rated conditions. Rated conditions, these are the rated conditions. This is the rated apparent power. The rated input power is apparent power S times cosine phi, the power factor angle. B, if the field current is kept constant, determine the maximum power the generator can supply. In this part, we say neglect RA. For the conditions in part B, determine IA and power factor. Draw the phasor diagram. Now, if we go to the first part, which is determine the excitation voltage and torque, we have Vt equal 14K divided by square root of 3 is 8083 volt per phase. The rated current is equal apparent power divided by 3 Vt. Now, if I was given this here in megawatt, then the rated current will be S divided by 3 Vt times the power factor. So you have to try to understand the difference between the two. Here is I equal S divided by 3 Vt. In the other case, if this was a real power, then I is going to equal P divided by 3 Vt times the power factor. And this is equal to 10 times 10 to the 6 divided by 3 times 8, which is equal 412.4. Power factor at rated power is given 0.85, so the angle is 31.8 and it's lagging power factor, so this will be negative angle for the current. Now, to find EF is equal to Vt, we have the resistance here. Take into account IARA plus JIAXS. Now, this is going to equal as vector, this is the voltage, this is the resistance times the current, and this is current times the XS reactance J, 90 degrees. If you solve this, then simplify this, change from polar notation to Cartesian, polar to Cartesian, and then the resultant is 14684.7 volt and 26.6 degrees. Delta is 26.6 degrees. If you remember from the last video, we said that the value of IEF depends on IF, and EF is rather high here. The rated voltage is 8000. The EMF generated voltage inside the machine is 14,600, and the difference is dissipated in the resistance and the leakage and the synchronous reactance. Actually, if you draw the phasor diagram for this case, then it will look like this. It will have this is the voltage VT, this is the current IA, and I have to get to EF, I have to add to IA to VT IARA. IARA is going to be in phase with IA. This is IARA, and the JXS, as I said before in the last video many times, when you multiply a vector by J, it will turn counterclockwise by 90 degrees. So this is JIAXS, and this will be EF, and this is the delta. Now, I'll ask you a question, I'll leave you to think about it. What would happen if we neglect RA? This vector will no longer be here. What will happen to delta? Will it be still 26.6, which we calculated earlier? Or will it be greater than it, or will be less? I'll leave you to think about this. Okay? This will show you the significance of these parameters when we take them into account or when we neglect them. So, we found the voltage, and we found the voltage, and we found the excitation voltage, and we found the power angle. Next, he wants the torque. To calculate the torque, we have to find the power. Torque is a real quantity. Torque is a real quantity, and the real developed power is the same as the input power, the rated power, because we have no losses to take into account. Now, P equal MVA times power factor. Remember, we have S equal P plus JQ. S the apparent power, P real power, Q is reactive power. And from this, we could deduce that P equal S phi cosine phi, the power factor angle. Now, this is P. This will be the developed input or developed power, real power, 8.5 megawatt. Now, the torque is equal to power divided by omega, and as you know, the synchronous motor or synchronous machine runs at synchronous speed, so I must find NS. NS is equal to 120F divided by P, and this is equal, for a two-pole machine, 3,600 RPM. Omega S equal 2 pi ns divided by 60, and this is equal 377 radians per second. And the torque will be P divided by omega S, which is equal 22.55 kilo Newton meter. The other part B, if the field current remains the same, is kept constant, Determine the maximum power the generator can supply. Neglect RA. This means if the field current remains constant, then EF will remain constant because EF is a function of the field current. So maximum power is always at delta equal 90 degrees. Sine delta, the maximum value is 1. So P max is 3 VT EF divided by XS, and this is equal to 3 times VT times EF divided by 20, which is 17.8 megawatt. This is the maximum power that the machine can develop. Next, we have for the condition in part B, which means RA is negligible, determine IA and power factor. Right. Now, IA equal VT minus EF, minus VT divided by JXS. And for maximum, for this condition, delta equal 90, so the angle here will be 90. So this is minus this quantity, the voltage, divided by J20. And this will be 14,685 divided by 20. The J will cancel with the 90. And the minus, we can think of it as J square. So J square cancel with one of them, cancel with J. So it should be plus J times 404.15. And this is the current. And the angle is 28.8. Therefore, IA equal 838.1 amps, and power factor is cosine 28.8, which is 0.876 leading. Now, this is the large value of EF, which means large value of IF lead us to a leading power factor. Now, we draw the phasor diagram. This is VT. EF, we expect EF to be 90 degrees, it must be. And so the vector EF equal VT plus JIAXS. Now, if you look at this triangle, this will be direction of IA, the current, and it will be at right angle to the vector JIAXS. Because IA, I multiply it by J. And we can obtain the angle, which we found here, just to check that our calculations are correct. This angle plus this angle is 90 degrees, and this angle plus this angle is 90 degrees. So this angle must be the same as this. So this is phi, this is phi, the power factor angle. And phi is equal to the tan inverse of VT divided by EF. And this is equal to tan inverse 8083 divided 14,685, which is equal to 28.8 degrees, which is the same, exactly the same as the value of the power factor angle we obtained from the EMF equation, which we used to calculate the current. This is the second example problem. I hope everything is clear for you. If you have any problem, you could send me an email. Wish you all the best. Bye.